And we should be live. Welcome everyone to another technical in-depth sort of live stream here. Today with Linus Torvalds ramblings here on some mailing list regarding Intel's AVX512. And ironically, I just yesterday, not making this up, I was researching also with our previous video FPGA RISC-V stuff, because on the RISC-V side there are two proposals, SIMD, single instruction, multiple data, and vector extension. And I just yesterday was researching which of those is now the favorable, and I wanted to make a live stream about this. So ironically, just now Linus wrote here AVX512 because here regarding to some article that some Intel Adler lake of all lakes here with this big little configuration doesn't enable AVX512, only AVX2. And of course this could only be the little cause of this ARM like little and big setup, but whatever. And Linus Torvalds chimes in here. He hopes AVX512 dies a painful death and that Intel starts fixing problems instead. Yeah, fixing problems, Spectre meltdown. Say greetings. Instead of trying to create magic instructions, to then create benchmarks that they can look good on, he hopes Intel gets back to basics, gets their process working again, like yeah, a process node, there was something, and concentrate more on regular code that isn't high HPC or some other pointless special case. Also, he said it before, he said it again, heyday of x86 when Intel was laughing all the way to the bank and killing all their competition. Absolutely everyone else did better than Intel on floating point loads. Intel's floating point performance sucked, relatively speaking, and it mattered not one iota, and because absolutely nobody cares outside of benchmarks. The same is largely true for AVX512 now, and in the future, yes, you can find things that care. No, those things don't sell machines, and also, yeah, maybe it's not entirely right with that one, but whatever. AVX has real downsides. It's much rather see that transistor budget used for other things that are much more relevant, even still FP math and the GPU rather than AVX512, or just give me more cores, good single thread performance, but without garbage like AVX512, like AMD did. Want his power limits reached with regular integer code, not with AVX512 power virus that takes away top frequency because people ended up using it for mem copy. And basically, mostly what I already said here in the previous videos, I oftentimes which is why I wanted to point this out specifically when this ramblings already come along. So already, not only me, but already two idiots of having here some similar opinion. I always said, not only, although I run here, certainly could have had this shameless plug open here, our build from source distribution, T2. Although I ironically not only main developer and stuff, so I, of course, literally compile all this stuff, but even I said this before already over 2 years here on this channel with my portable SSD that I plug into each machine. So I said this before, I don't have like a local installation except my data center and stuff. But when I just work on something, I have here one SSD, just don't want to touch it too much right now anyway, and you'll know how an SSD looks. And I said this before, it is super annoying. So on this SSD with T2, with build from source, I only compile to core 2 of all old-fashioned garbage for the simple reason when I want to, if I use this Horizon or whatever for other machine learning purposes here, for our project and stuff, then I just use an old MacBook or something, and then it might have just a core to do, even because they're thin client, whatever, thin client, and it's super annoying. Or data recovery or the other tinkering, like weekend projects of tinkering on hardware support, with optical SPDIF stuff and all the other previous projects, and so it's super annoying for me, even though I could like literally optimize all my system with T2, just some configuration flag away, optimize for latest and greatest AMD Zen 2. I don't, because I want to plug in this in other systems, and that is also the issue for you playing along at home and all the big vendors like Microsoft, Apple, and SUSE and Reddit and stuff. So all the problem with AVX, and I said before, especially in my microkernel series, is where I have some pipe dream concepts of how we could potentially maybe make this entirely better, the whole software stack. I said it before there, if you statically compile stuff like you download Firefox, you download Windows, macOS, SUSE, Debian and so on, they barely use all these fancy SIMD instructions because you need to specifically program for those. Many of you of course know this, and welcome everyone, recurring fans there. But this additional instructions, they do not magically, some people think they magically make this faster. Intel AVX ISA, we had here a previous video if you want to watch all the details, and if you're new to this channel you might want to share, like and subscribe and watch the previous videos. There's also instructions at architecture, and of course when you want to download it you don't find it, because these are like special instructions and they are not like magically used. So like all the move, again previous video, cosinus and whatnot, load integer and multiply. This special instructions, if you're new to this stuff, someone needs to write them. So if your processor has AVX512, it doesn't make it a single bit faster. So you're spending 100 millions or probably billions of logic gates there for stuff, for AVX512 stuff that is barely used. Only if you load a special application like maybe Blender or some AAA game, or you build your own Linux distribution, then this stuff is used. And I said this before, in my opinion, not a very good use of silicon space. Yeah, so how do you use this? You either need to write special assembly code because they are complicated, and yes, that's still a thing if you look in open source projects, FFmpeg, other like glibc and the Linux kernel. So people still write assembler for multimedia stuff because this stuff is very specific stuff. So this is like load 8 words or stuff and multiply for like a matrix and so on. So very specific stuff that doesn't even fit for normal programs. So you need to have massive parallel number crunching for these instructions even to make sense. And then they are not used magically. You need either the programmer in assembler or the compiler, like a fancy latest and greatest like GCC and Clang, automatically optimizes. Even the automatically optimization often not the very best, but yeah, there's only so much a compiler can do with C code. The other problem, just like Linus mentions here, the clocks, you might have seen this with all the YouTube overclocking and frequency measuring goodness there. If you run this AVX heavy stuff, you get less turbo boosting, and so even when your program uses AVX a little bit, and this is also what Linus Torvalds means here with people used it for memcopy, stupid. So use it a little bit for memcopy, and this memcopy might be tiny little bit faster, but your whole program is slower because it doesn't reach the same turbo frequencies anymore. Completely stupid, right? So apparently they, at least here according to this wiki chip specification, you certainly have seen this in other Intel slides and YouTubers benchmarks, the more AVX2 and 512 heavy workload you have, the less turbo frequencies you achieve. Example workload, so non-AVX, SSE, light AVX2, integer vector, non-multiply, also yeah, integer vector, non-multiply, thank you very much, or regular instructions, like absolute highest frequency, like turbo frequency, but as soon as you use AVX2 heavy, like all AVX operations, light AVX512, non-FP, integer vector, non-multiply, then you get here less frequencies. And if it's 512 heavy, like all the other 512 AVX512 instructions, including multiply and stuff, then it's yeah less. Even sometimes at some processors probably not even the base clock. So there is like, as far as I remember, yeah, non-AVX workloads, and this base frequency, non-AVX base frequency with some processors might actually sometimes be higher than if you have AVX heavy workload here. Then this might be a does this even SSE base, AVX base? So as far as I remember, anyway, it can even, as soon as you use AVX heavy, it could even potentially be slower than non-AVX base frequency. So from all of this, so we are spending, in my opinion, it makes totally no sense, totally agreeing there with Linus Torvalds. And for this reason, spending there 100 millions, if not billions, with all the many cores on logic gates for stuff that is rarely used, and if you use it, then you get a massive frequency penalty because thermal budget and stuff, and then it's not even that easy to use. How could we solve this? So not only in previous live streams of my microkernel dream system series of maybe we should just JIT all the stuff like fancier than Java, because 2020 certainly learned a couple of things since the days of Java. So then you would solve this of having a pre-installed system similar to Android, runtime of ahead of time recompilation on your phone there for all the specific ARM cores, similar to this, because then I boot my system, or you download Windows, and you during the first use, and whatever the case might be, have this optimized for your processor, whether you're running an old-fashioned Core 2 or Core i7 from 2nd gen or whatever, or latest and greatest with other instruction set. And maybe here the whole instruction set should be different. That is what I was researching yesterday in terms of RISC-V development, and Dieter agrees 1024 cores. And this is the question I wanted to ask. So first of all, you rarely use it, AVX512 rarely used. And so if you have this logic gates, I would rather, so the whole day I'm running here with certain here AMD EPIC thread-ripping Ryzen performance. So 32 threads, as you can see here a little bit at the side. 32 threads right now, most of them idling, even OBS and stuff, barely loading this. 32 threads. So if you ask me, you have like, do you want 32 threads or 64 threads and no AVX? I would say, give me the 64 threads, because I barely use AVX 512 and stuff anyway. So in my opinion, totally agreeing, all those logic gates, all those transistors and stuff, much better spent, rather give me twice the cost. Stupid, but yeah, marketing. So how could we do better? And that is the nice thing about RISC-V, that this is some independent researcher effort of all universities and companies and students and hobbyists worldwide. So they came up with a much better way. It looks like most likely RISC-V Vector most likely wins here in terms of becoming the favorite to be implemented, because there's also RISC-V single instruction multiple data. Actually could have opened this. So there are two competing extensions. One is single instruction multiple data, also whatever. But today I wanted to shortly also present this vector. So this is what I researched yesterday also. So the motivation is of course to bring like single instruction multiple data like to RISC-V, latest and greatest open stuff that we also can. I hold this probably. Let's just unplug here some live here on this channel, only ripping some connectors of this precious board. Here ULX 3S of our RISC-V uses fun previous videos. So what they have done, they of course they researched this. What researchers do, they research, right? And they came to the conclusion that SIMD single instruction multiple data instructions considered harmful. Like, yeah, no surprise here. Basically agreeing with the two idiots that are Linus and myself. And so what is the difference? So vector instructions already done in the 60s and stuff, even Cray and other vector machines, so all the Cray supercomputers there with vector extensions, so not invented in RISC-V, but good old-fashioned stuff. And that is also the difference between a company like Intel just hacking something and independent worldwide researchers researching and coming up with a potentially better, if not best solution. So they analyzed here MIPS, either single instruction multiple data versus vector. It's slightly different, you will see in a second. So this is assembly that is they generated here either by hand or compiler, maybe compiler. And so this is how MIPS MSA looks. Intel AVX2 here with push move here vmove SD, so move whatever XMM1 register here of stuff, ddub whatever, duplicate or something. Yeah, you see instruction stuff where even from a first glance, whatever they do, it's like some collection of random characters. So RISC-V RVV, RISC-V Vector extension here, and of course we don't want to look in this assembly. You can certainly do that at home, but much more interesting is the table they compiled here. So the instructions here needed for this loop, the AVX512 of size n, double A, double x and y, for the size here, multiply with some fixed factor and xy plus xi plus yi, just here whatever that is used for, something that's a regular vectorizable code. And surprisingly, if you do some research and like model it and make some simulations and think about this and stuff, the least instructions, right? So the leader of x86 market share solution, 29 instructions, MIPS 22 instructions, and RV32V 13 instructions. Instructions per main loop, although the most here, but bookkeeping instructions. So bookkeeping meaning like counts, keeping does information you need for this code, like end of loop and how much you advanced and stuff. So results per loop, results per main loop, 2 results, for results 64 freaking results. Instructions per dynamic n here of supplying n with 1000, so MIPS case 3511 instructions executed. Intel AVX2 1517 instructions executed, and RV32 vector extension are only 163 instructions. So can you do better? Apparently these researchers think yes. Of course we need some silicon and stuff, and of course it could be a very, I certainly don't have this, maybe would be a fun project to synthesize it on this FPGA, right? But would be interesting to play actually along with this and how real world code, not like one DAXPY function, but like comparing more functions. But I think I saw some study, not sure if it's in this document, but maybe another. And if they research here more code they have here. So how does it work? This works, there's also some other stuff. So benchmark performance. So here's some MXP. This is some other special. I've tried to find this. I didn't really find too much about this MXP. That appears to be, as far as I found, some other softcore, like maybe some vector specialized softcore thing, whatever. But they combined here. I'm not really sure why they didn't compare here x86. It's slightly unfair that they didn't have this in here. Not sure what they are hiding there, but yeah, never benchmark when you didn't benchmark it yourself. But ARM, Neon, and RISC-V performance here allegedly. Do they also have maybe not? So yeah, some different benchmarks to the FIR, Zobel. Here some different stuff. The picture here is similar. RGB Lumar, so not looking too bad, right? Not too shabby. For those people who always ask me, when will RISC-V take all the stuff over? My prediction is, as so many people working on RISC-V and putting not only of some stupid YouTubers, but like real researchers doing their research and putting all their efforts here together. Everything I've seen from RISC-V looks pretty amazing, and I can't wait to have more high performance silicon. Would be interesting. I would actually recommend for AMD. AMD had some mentioned this before. You might have seen this Zen with ARM front-end Opteron A1000 project. Somehow they've canceled this for some reason, not really sure what. I would actually recommend AMD to prepare some Zen-based RISC-V series. Just slap an RISC-V front-end to that. That would be pretty cool. And what else do they have here? So they have here some maybe written here with some in strings RV stuff here, V multiply something. Did they had somewhere, not really sure. So they have here basically some more code details for like 2D filter here of matrix manipulation. Underlying here their findings a little bit sad that they didn't have Intel here, but no, whatever. It's the best I could find. And yeah, certainly this looks pretty amazing. This is also how this would look like in case you're wondering of in strings for the stuff. And so what is the difference? And this another thing that you might not have found. So for those who stayed here, for all those people tuning in live, and you made it to this point. So what is so cool about this is, it's actually not in this slide. So the cool thing is that this is also better future safe, because let me just find here some other document. Because the benefit of this vector extensions also is that it allows for flexible expansion. Let me see, I yesterday found here some other stuff. Let's see, is it on this? Not really entirely sure. Some other blog post, because you can flexible set the width. So your processor might implement some vector width of 1024. Let's just pull you some ballpark number. And so the nice thing is, or the problem on the Intel side, on Intel you might remember first Intel did MMX, the multimedia extension there in 1996ish or something, in the first Pentium, or the second or third Pentium, so basically the last Pentium update. Then they AMD did 3D Now because patents and trademarks and stuff, which actually was somewhat better, unsurprisingly. Then Intel did SSE, the streaming data extension stuff there, or internet and streaming, whatever the stupid name was. And later then SSE and SSE2 and SSE and SSE3 and AVX. And the problem is, on the Intel side, that each time Intel comes up with a new freaking fancy extension, you need to recompile or write new assembly code. And with this vector extension, you can even have a wider vector processor. Like, think next year you have a RISC-V CPU with 2048 or even 4K, like 4096 or something, similar to this new VIA processor maybe. And it automatically works still and makes this code faster, because the code can iterate over the full vector width. So you run this code. Let's see, was it this what I saw yesterday? Yeah, probably here. This might have been so vector length specific here, just what I said. This actually might be similar to what I've seen yesterday. Here of MMX, 64-bit registers, SSE 128-bit registers, AVX 256-bit registers, and AVX 512. Obviously, it's already in the name, 512-bit registers. And just as I said, it's not backward or forward compatible. And the solution here is agnosticism. So what this means, as I said, it has some vector width, and such vector instructions that then split this into whatever your code needs of vector size, and like here 128 bits, so meaning that the vector length, VL for vector length obviously, up to a 8-bit wide E8 elements is requested while the instruction returns the resulting length of register T0. Thus, if A2 register is set to say 4096 on a CPU with a vector register length VLang of 128-bit, the following vector instruction works on 16 elements wide vectors, and T0 is thus set to 16, while on a CPU with 512-bit registers the vectors are configured to be 64 elements wide, and T0 is set to 64. And when you see this kind of research and stuff, certainly I've never personally owned a Cray. Maybe one day I want to share, like, and subscribe. Maybe in a couple of years we get ourselves here some Cray for having a nice bench work table. Not having researched this Cray stuff, maybe this is similar to how the first Cray supercomputer, vector computer worked also. Not sure, maybe. But when you see this ingenious stuff, actually, then you wonder what the Intel engineers, well, certainly the engineers at Intel were doing some random stuff. Some manager said, hey, we need some multimedia stuff, or I don't know how they came up with this. But if you see such flexible stuff, you're wondering what the heck were all the big vendors doing for all the years. And this is so much more amazing when you can upgrade your RISC-V CPU and the code runs like twice as fast without even having to touch your freaking assembly or even compiler. This is so much cooler. Can't really wait to work with this. So much more advanced and stuff. And this is also when people always patents and innovation, and it's like, yeah, what did Intel making some shit up and pressing it into the market with their marketing money, instead patents and marketing money doesn't help a thing for innovation. And yeah, research and more research and working together on certainly open solution. Pretty amazing stuff. I'm pretty thrilled when I see this here. Of course, I haven't worked yet with this. Probably I should try to get some FPGA stuff for that. But this looks really promising here, in my opinion. Maybe you want to take a look at yourself. There are already some patched tool chains with support for that. Technically, binutils are sufficient to sample examples. So yeah, if you want to play along with this, there are some patches for LLVM, Clang, and GCC binutils, and certainly maybe already some FPGA, Verilog, or other kind of softcore stuff floating around. If you have any comments to this, leave in the comments below. In my opinion, so much more amazing than Intel's fixed stuff there that is incompatible and forward and backward incompatible. And yeah, even if you use it, then frequency goes down because thermal and budget and power budget. And also another thing I actually wanted to say, that this the Intel logic gates, there are 100 millions of, you could actually check how many would it be in terms of Intel Core Gen 10, how do they call this usually, transistors, or where do they have here maybe some ballpark number of billions. Thank you very much. I wasn't interested in nanometer plus, but certainly billions, and many billions of them maybe. And Intel is also, so this, you should also keep in mind that this stuff is coming from a time when GPUs were not flexible programmable. So I also wanted to add here to Linus' ramblings that this kind of stuff, AVX512, it's maybe not even recommendable and most usable to have this in your CPU when this is this massive parallel workload stuff that you probably rather want to do in a GPU. There's a difference why GPUs are so different, because they have this massive parallel array of 4,000 or so compute elements, and for massive parallel data processing, maybe just don't use a freaking CPU at all. And this comes from a time when we had Doom and Quake and not even many 3D accelerators, certainly the very first here on this Voodoo and Verge on, and Rinchen Verite here on this channel. But these GPUs were of course not flexible programmable, as they also didn't have any video acceleration for MPEG videos or stuff. And of course, in the first days of Intel MMX, there was nothing else. Okay, fine. But in the meantime, we also have much more powerful GPUs. And of course, the first generations of GPUs, they were fixed function. Well, except the Rendition Verite and maybe some other special purpose stuff. But certainly the NVIDIA and ATE Rage and stuff. And since the advent of GPU, general purpose GPU programming, that came around somewhere like a decade ago, and that is with also when Apple, like in Mac OS 10.6 introduced OpenCL. Let's just this. And since that days, since you can flexible program GPUs, because previously they were, as per the previous videos here, fixed function of let's shade or texture, or usually texture anyway, texture and multi-texture and bitmap and lightning and light triangles. Since those days, since we can run programs like not fixed function, but let's texture this data in GPU VRAM with this kind of algorithm, and we can also use it for hashing, like cryptocurrency, which I, by the way, don't recommend, but other AI, neural network and other stuff. It's probably total waste of silicon anyway, because you usually have a GPU, and this kind of stuff, when you have this workload already to start with, it is much more useful and performant and power efficient to do this on your special purpose massive parallel number crunching thing that is your GPU instead of your CPU. That is should be more designed for general purpose in like bookkeeping, general program flow. So history, what do they write here? History something 2000, what became popular something. So GPU, whatever. It's all not what I wanted. Floating point numbers, vectorization. Do they not have whatever? Not really what I was looking for. But do they not have a year? Probably this was around 2006ish. Oh yeah, NVIDIA CUDA. There you have it. Implementations of OpenCL. Of course, these are only the languages of exactly generating with OpenCL and now Vulkan. Exactly this code for the GPU, because certainly not only does NVIDIA not disclose it in full anyway, but you anyway don't want to write your GPU program specifically for one NVIDIA CPU. This is why you use OpenCL or Vulkan and other stuff to have this runtime compile it for your specific GPU model, because they are all different. But yeah, if you have something in your CPU, again, this kind of stuff, massive parallel stuff, GPU, because GPU, and otherwise maybe something like RISC Vector extension looks much more promising in my opinion. Leave in the comments below if you have any comment to that, if you tried RISC. Do we even, where is this now? This nice block that I had here a second ago. Whatever. Then let's have this closing slide. Anyway, if you have any performance data or played around with this, leave in the comments below. But they also see how much better you can do this if you do this in an open community than one vendor dictating their patented stuff. I hope you learned something and found this interesting. Hopefully additional knowledge around Linus Torvalds rumbling here, who is grumpy, but somehow Linus Torvalds usually is similar to ourselves here. Anyway, that's it for today. I hope you learned something. Core wrote how feasible only vector extension CPU would be, like Cray style. Yeah, not only vector extension, of course not, you still need the general purpose stuff, but this RISC-V stuff, if you want a vector extension, this RVV RISC-V vectors looks highly promising. And otherwise, Detard wanted 1,000 cores, similar to myself, preferable at a terahertz, yeah, obviously. Similar to, I actually checked this yesterday, there was this new VR CPU. Actually, ironically, I had hard time to find it, except on my own channels. 2020, you find this the easiest using your own YouTube channel. Because VR also came up with this AI coprocessor stuff, and this looks a little bit similar to the vector extension. Maybe they, maybe NVIDIA, maybe VR. Oh, so I need to fix the description here. This description is not the best. So much to your hobby YouTube channel not having the most polished comments here. But where would this be? Here, Centaur. And this vector stuff here looks a little bit like the RISC-V vector stuff of one very large vector that you can configure in different slices. So maybe Centaur saw this RISC-V stuff and thought, wow, that is actually more amazing and saves us some patent issues with Intel. And one thing, because they have here some 32 freaking bits, very wide SIMD architecture, organized in vertical slices. Sounds a little bit to me like this RISC-V stuff. And that one thing they write here, and that you should also keep in mind, it's not as easy to just synthesize here your RISC-V stuff here on some FPGA, because one thing that we also noticed ourselves, memory bandwidth and caches and stuff, previous video, for performance and more performance. And one thing you see on this VR slide is that they particularly mention here memory bandwidth. And certainly if you have such a 16K, was it 16K, right? 16K bit vector, or even 32K bit vector, and actually it becomes a challenge to challenge memory. Many millions of bytes required to processing an image and video stream. There's lots of 20 terabyte second internal RAM required, plus fastest possible access to DRAM and S3 cache. So yeah, if you're going with this, you see this also with GPUs, even just loading this in your RISC-V core. So yeah, you certainly need quite some cache and memory interface bandwidth stuff for sustaining here some 1 kbit vector load store multiply stuff. But anyway, just a tiny little tip if you wanted to play along at home. So yeah, that's it for today. I hope you learned something. And space heater and stuff. Yeah, cool stuff. Thanks for tuning in. I hope you learned something. We can continue with other tinkering and stuff, and certainly more code and RISC-V. And anyway, wish you a happy and sunny Sunday, and to see you soon for the next videos and live streams to come.